In this video, we're going to talk more about vectors, specifically the dot product. Now that we have a way to represent vectors algebraically, we can define a type of multiplication between two vectors. If you'll remember, the only type of multiplication we've done so far is taking some vector and multiplying it by a scalar, and we've been able to distribute and so forth. But now we want to see how we can multiply two vectors by one another. Now, there's two kinds of vector multiplication. We're only going to talk about one kind, that is the dot product. And later on in your math career, you'll learn about the other kind of vector multiplication. The dot product is also called the scalar product, and that's because when you multiply two vectors using the dot product, the result or the answer that you get back is a scalar. So you don't get back another vector, you get back a scalar. So here's the definition. If you have vector A with components A1 and A2, which you could write A1 I hat plus A2 j hat, and then you have vector B with components B1, B2, which you could also write as B1 I hat plus B2 j hat, we say that the dot product of A and B, which is denoted by putting a heavy dot between A and B. So normally in math you see a dot as multiplication, but this is more bold. And the dot product is defined to be the following. So if you have vector A dotted with a vector B, you take A1 times B1, so both of their x components, multiply them, and then add that to A2 times B2, the product of their y components. So you could see the result is going to be a scalar because you add these two values together, you don't get back a vector quantity. Okay, so let's look at an example here. Find the dot product of the vectors, and they give me vectors A and B. So this is A1, this is A2, this is B1, this is B2. So by definition, A dotted with B is going to be A1, which is -2, times B1, which is 4, plus A2, which is 5, times B2, which is 2. So you take the x components, multiply them by each other, take the y components, multiply them by each other, and then add everything up. So this is going to give us -8 plus 10, which is 2. And see clearly this is just a scalar quantity, not a vector. All right, let's look at another example. Here A is 4i hat minus 2j hat, and then B is 2i hat plus 7j hat. So A dotted with B is going to be 4 times 2 plus -2 times 7. So that's going to be 8 minus 14, which is -6. Okay, now that you know how to compute the dot product, what is it used for? Probably one of the most useful applications is the following theorem. So if theta is the angle between two non-zero vectors A and B, then A dot B is equal to the magnitude of A times the magnitude of B cosine theta. So here we are able now to find the angle between two non-zero vectors. So say this is vector A, this is vector B, and theta is the angle between them. Well, I can figure out the value of theta by using this theorem here. Okay, good. So next example, find the angle between the vectors A and B. Okay, well, if I'm after the angle, then I want to isolate cosine theta in this formula here. So cosine theta would equal A dot B divided by magnitude of A, magnitude of B, right? So A dot B, that's -2, 5, 4, 2. We actually already have that from earlier, but I'll rewrite it. So it's -8 plus 10 over, now magnitude of A, remember we take the square root of the sum of the square of the component. So it's going to be the square root of 4 plus 25. That's magnitude of A. And then magnitude of B is going to be square root of 16 plus 4. So cosine theta is equal to 2, -8 plus 10, over square root of 29 times the square root of 20. Okay, which means theta is equal to cosine inverse of, well, square root of 20, that's 2 rad 5. So these 2's can cancel. So I have 1 over rad 29 times rad 5. And since I'm just after the angle anyways, I'm not going to worry about simplifying this any further. Just punch it in your calculator, take cosine inverse of that quantity, and let's round to 2 decimal places. This is approximately 85.24 degrees. Okay, and the great thing too about this theorem is that if your angle is greater than 90 degrees, then you'll be able to compute it, no problem, because we know cosine inverse will give us values between 0 and 180. And you would actually know that the angle between 2 vectors is obtuse, greater than 90, if the dot product between them is negative. Okay, moving on, let's talk about parallel and orthogonal vectors. So we're going to still let theta be the angle between 2 non-zero vectors A and B. We say that A and B are parallel if theta, the angle between them, is 0 or pi, 180 degrees. And that A and B are orthogonal if theta equals pi over 2. So allow me to draw you a picture. So here's vector A. And say the angle between vector A and vector B, the angle between them would be 0 degrees, right? Or 0 radians. And you could see, I could even put B right on top of A. They're parallel. Now, if theta is pi, all that means is that they're moving in opposite directions, right? Because the angle between them is 180. So here would be A, and then, can I bring back B? No, it doesn't remember it. Okay. And then say this is vector B. In this case, theta would be equal to pi because they're moving in opposite directions, and you could see the angle between them is 180 because the arrows are pointing in opposite directions, okay? Either way, they're still parallel though, right? And then orthogonal is if the angle between the 2 vectors is pi over 2. And you're probably used to calling this perpendicular. And there's a little bit of a difference in the definition, but right now when we're just dealing with vectors in 2 dimensions, you can think of it pretty much the same way. Okay, so that's orthogonal vectors. Theta is pi over 2. And then here, these are parallel vectors. Okay, so show that the following 2 vectors, A and B, are orthogonal. Okay, if they are orthogonal, this means the angle between them is equal to pi over 2, right? Or 90 degrees. And we have our theorem. So by our theorem, cosine of theta, which is the angle between them, would be 0, which is what their dot product should equal, right? I don't have to worry about dividing by the magnitude because both of these vectors are non-zero. So their dot product should be 0. So anytime you're asked to check if 2 vectors are orthogonal, really what you're asking or being asked to do is to find that their dot product comes out to be 0. It means the same thing. All right, so we're just going to take the dot product and check. So vector A has components 8, -4. Vector B has components -6, -12. So let's just compute this dot product. So A dotted with b, that's going to be 8 times negative 6 plus negative 4 times negative 12. So 8 times negative 6, that's negative 48, plus positive 48, that's 0. So we're good to go. Okay? Good. Next example, show that the vectors A and B are parallel and determine whether they have the same direction or opposite direction. Okay, so let's rewrite them. So vector A has components negative 5/2, 6, and B negative 10, 24. So again, cosine theta is equal to A dot B divided by magnitude of A times the magnitude of B. So let's see what A dot B is going to be. So negative 5/2 times negative 10 plus 6 times 24 divided by the square root of, if I square 5/2, that's 25 over 4 plus 36. And then magnitude of b is going to be square root of 100 plus 24 squared, whatever that is. So in the numerator, I'm going to have 50 over 2, so that's 25, plus 6 times 24, that's 169, over the square root, let's see, so 36 times 4, that's going to be 144. 144 plus 25, that's 169 over 4, times the square root of 100 plus 24 squared. And all of this simplifies to 1. Okay, so if cosine of theta is equal to 1, then that means theta is equal to 0. So we can see that clearly the angle between them is 0, so they have the same, they're parallel. And then they're asking us to determine whether they have the same direction or opposite direction. Well, if they had the opposite direction, theta would have been pi or 180 and cosine would have been -1. Another way to tell is look at the components. So for A, it's negative 5/2, 6, and B, the first component is negative as well. So since both of the first components are negative, you can tell that they're headed in the same direction. It would be opposite if maybe B was positive 10, negative 24. Then it would be opposite. You see how the signs are switched? Okay, good. So we have a theorem now, which we've kind of explored already, telling us that two vectors A and B are orthogonal if and only if their dot product is 0. Okay? So here we're just going to look at an exercise applying this theorem, and it says determine or find M such that the two vectors given here are orthogonal. So they're telling me in the problem vector A has components 5m and 3. Remember, I hat and j hat are just those unit vectors. And then vector B has components 2 and 7. And they want me to find M so that A and B are orthogonal. Well, if A and B are orthogonal, then by our theorem, A dot B should equal 0. So A dot B would be 5m times 2 plus 3 times 7, and I'm going to set that equal to 0. So 10m plus 21 is 0, which would mean 10m equals negative 21. So m should be negative 21 over 10. Okay, so that's just applying the idea that if two vectors are orthogonal, their dot product is going to be 0. All right, and then just a couple last exercise. Given vectors A, B, and C, find the following. So we need A dotted with B minus C. So B is here, C is here. I'll write it out. So B minus C is going to be 3, 4 minus negative 1, 5. So this is going to be A, which is 2, negative 3, dotted with, well, 3 minus negative 1, that's 4 for the first component, and then 4 minus 5, that's negative 1. And then I'm going to compute this dot product, so this is 2 times 4 plus negative 3 times negative 1. So this is going to be 8 plus 3, which is 11. Okay. Next, we have A dot B minus A dot C. Okay, so we do the dot products first and then subtract, kind of like our normal order of operations. So A dot B, how comfortable are you guys? Can you do it in your head? A dot B is going to be 2 times 3 plus negative 3 times 4, so that's A dot B, minus A dot C is going to be 2 times negative 1 plus negative 3 times 5. So this is going to be 6 minus 12 minus negative 2 minus 15, which is negative 6 minus negative 17, so negative 6 plus 17, which is 11. Oh my goodness, we got the same answer. That's because they were trying to demonstrate that A is equal to B. So we have a distributive property here. So A dotted with B minus C, you're allowed to distribute the dot product over addition or subtraction, and that's why you get the same result as A dot B minus A dot C. Isn't that fancy? Don't worry, I'll let your future math teachers cover more properties of dot products, but this is just a little taste of what's to come. Okay, that concludes the lesson. Hope you enjoyed it.